So anyway, Paolo is doing this morning's keynote, and is an Italian guy, brilliant. He's wrote the metaprogramming Ruby book, a really interesting fella, and I think now that you're all here, you're awake and ready to be inspired. I really think Paolo's an excellent choice for us all to get the day started. So please put your hands together and welcome to the stage, Paolo Perrotta. There you go. We have to shake hands. We go back over there. We hug. It's going to be awesome. All right. We're efficient. We're organized. No. We have to shake hands.
Okay.
Would you don't do that? We kiss. How do you want to do it? You want to go back? Want to come out?
Do I have to? Can we do that in the backstage?
We're going to do it in the backstage. All right. Follow. That's good.
Okay. Here is something I read on a book once. The evolution of programming languages. First, there was machine code. We were basically programming with numbers. Okay? Then somebody had the idea of attaching names to those numbers, and we got assembler. Then we kept building over it. It was a steady progress, so we had high-level languages, in particular procedural languages. And then it got more and more abstract, and we got object-oriented, which is pretty much like the current golden standard. Question for you, what's next? I mean it. Functional languages. Sorry? Okay. Okay. I'm not going to comment on you. I'm good with anything. What? Okay. I heard a few interesting suggestions. A few people said functional languages. That's basically Lisp, okay? Some Lispy stuff. Basically, it is Lisp. Come on, you look at functional language. Those are the concepts. Do you have any idea? Don't say that. Do you have any idea how old Lisp is? Don't say that. Sorry. Well, don't tell to people who don't know because you're getting close, okay? Just think. Is it because we know it's old? Is it like from the 70s? 60s? I have a hint. Elvis Presley joining the army. 1958. Okay? So you're telling me basically that a language from 1958 is the next big thing. This is probably older than your dad, 1958. Doesn't add up, doesn't make any sense, frankly. I mean, this idea of building more and more abstraction on top of machines, it doesn't really work. This beautiful upwards arrow, this progress, that's not the way progress works. That's not the way innovation works in general. We can tell this story, but it's fake. Innovation is a mess. And because this is a keynote, I'm supposed to be kind of fluffy. I'm not going to talk about software for a while. I'm going to talk about a story that has to do with innovation. It will take about 15 minutes, so get comfortable. And it's the story of how humankind found a way to calculate longitude. You might have heard about it, but chances are you didn't. And I find it quite amazing, actually. So because we're in Catalonia, I want this story to start in Spain. And that's the place that Christopher Columbus left from on his first famous travel, Palos. And Columbus wanted to reach what he called India, which was actually Asia. He said India to say Asia at large. He wanted to go to the east coast of Asia. He wanted to reach Japan, basically. That was the plan. Okay? There is this notion that Columbus wanted to prove that the Earth was round. That's a legend. Everybody knew the Earth was round. The ancient Greeks knew. They actually calculated the size of the globe with some remarkable precision. What Columbus wanted to prove is that he could reach Asia by navigating westwards. And other people were saying, no, you can't, not because it's theoretically impossible, because it's practically impossible. You will die before you get there, because there is a lot of ocean in between. They didn't know there was that stuff in between. So they said, you have to navigate for months on end, and you cannot do that. You will die of scurvy. Scurvy is an illness that is basically a lack of vitamin C. And if you stay out at sea for like 6 months, you lack vitamin C, so your body cannot synthesize a protein that's called collagen, and it keeps your tissues together. So your body basically decomposes from the inside. It's kind of quite splattery. And actually, millions of people died because of that. It's an illness that can be cured by drinking lemonade. But you cannot bring lemonade or lemons or anything like that on a ship for 6 months. So why did Columbus want to do that? Well, because he was basically delusional. He was very stubborn. You might say he was a moron, really. I'm sorry. But he was convinced that the Earth was much smaller than it actually was, for whatever reason. He thought that Japan looked kind of like Australia. So he said, oh, I will just get there. I will show you. Ha! And then he tried, and instead of dying, as you could expect, he stumbled over the Bahamas, basically, okay? And he went back. And he kept saying, oh, I went to Japan. People couldn't really believe that, so they started fighting. And eventually, they found out that he had discovered the continent. There were people there, but you know, as the Europeans, oh, yeah, it's new. We'll just kill everybody. So what happened is, well, you probably heard this story. If you grew up in Europe or the US, you heard this story many, many times. And if you were like me, you know, little nerd, then you grow up. At some point, you look at the map like that. You look at this, I think. You look at the distances, right? You think, was this guy drunk? I mean, look, he wasn't even 1/3 of the way through. And then he comes back and he says, oh, I've been to Japan. It makes absolutely no sense. If you don't know where you are at that level, how can you even think of crossing an ocean? Why don't you, I don't know, drift into Alaska and, I don't know, hit an iceberg or something? And actually, it's quite surprising, because if you look at the reason for that, he didn't know where he was, indeed. There is a story behind this that is, it requires us to understand how to calculate your position on Earth. The ancient Greeks said, let's just build a grid, okay? And we can use this grid to mark our position on the globe. And maybe you know that the vertical lines are called your latitude, and the horizontal line is your longitude. Okay? How do you calculate your latitude? It's kind of easy. You take a fixed reference point, like the North Star. It's almost exactly over the North Pole. And you, for example, look at the angle. Let's say that you are there, okay, there in that corner. And you look at the angle that the North Star makes with the horizon. You calculate that with a tool that's called the sextant. And as you move around, north, for example, you see the angle is changing. Well, the star seems to be rising in the sky. So you can check that and say, this is my latitude. That's easy. Now you need your longitude. Why don't you do the same? Of course you can. You do the same. You can find a reference point just above the equator and do exactly the same thing. But yeah, you probably see that there is something missing here. Voila. The stupid planet is rotating. No, America. Okay, I see. You are used to being right at the center of the map, right? Okay. No worries, so you are still there, only on the other side. So yes, the Earth is rotating. So you have another variable, right? Not a big deal. You need to know the position that the Earth is in at the moment. How do you know that? Yeah, fine. You find a specific reference point like Greenwich, UK, and you need to know what's the time in Greenwich, and then you know what your longitude is. It's that simple. There is only one problem. They didn't have clocks. I mean, they did have sand clocks, water clocks, solar clocks, stuff that doesn't work on a ship. Even in the 18th century, they invented the pendulum clock, and pendulums and ships don't mix. That was the problem. That was it. Okay? Now, it doesn't sound like a big deal today, but calculating longitude was one of the greatest scientific adventures of mankind. Seriously, it makes so many things that we consider huge look like irrelevant. The internet, it was a very small thing compared with this. The Manhattan Project, a bunch of nerds in the desert. It was really, really huge. For 2,000 years, since somebody proposed the longitude, to the moment where they could calculate the longitude reliably, basically every single great scientist of humankind tried this. You name them, Galileo, Euler, Newton. They spent a lot of effort to calculate the longitude. In fact, people said discovering longitude to say doing something that is impossible. Why was it so important? Well, they were actually dying. This is a picture of the Scilly tragedy in 1707. An entire British fleet was lost at sea on the rocks because they miscalculated their longitude. Thousands died. It happened all the time. It was a mess, even from a geopolitical point of view. You discover an island, then you lose it. Can you believe you can lose an island? It happened all the time. And then somebody else discovers the same island, but maybe a different country. I can let you imagine the bickering that followed. It was a huge problem. Basically, it was the bottleneck to knowing the world. So they tried pretty much everything. Okay? This is a very quick recap of a few methods they tried. They tried magic. They called it like alchemy, but it was magic. For example, there was this notion that I can take a sword and I can wound a dog, and then I can use this powder, and when I put the powder on the sword, the dog will feel pain. So we can keep the sword in Greenwich or wherever, and you can take the dog on board, and every day at 5 o'clock, I put the powder on the sword. I don't think they ever tried it, I'm glad to say. No dog was hurt, as far as I know. They couldn't really make the powder. A slightly more scientific way was called dead reckoning. Dead reckoning is simple. Basically, you just calculate your velocity, and then you calculate your position based on your velocity. So, for example, you drop something in the water, and this something floats away, and you measure how fast it floats away, and then you have your velocity. And then, from the velocity, you calculate how much distance you covered. Of course, the You make mistakes, and the mistakes add up over time, so it's really not very precise at all. It kind of sucks as a method. They tried to use the Earth's magnetic field. It's not, the magnetic pole is not really aligned with the geographic pole. There is an angle. You can use that angle to kind of understand where you are. But there are local variations, so it's all over the place again, and it didn't work. Most ideas that kind of worked had to do with looking at the sky again. So, for example, Galileo discovered the moons of Jupiter. And he had the idea that by looking at the configuration of the moons, you could understand where you were. But there is a problem. The moons of Jupiter are kind of small. You need a telescope. And telescopes, ships. So he came up with this wonderful design for this device. Look at this beauty, okay? This guy is wearing a helmet that has a telescope embedded inside the helmet so that it stays, basically, it stays fixed. Okay, and it's sitting in an hemisphere that is floating in oil inside another hemisphere. So as the ship yanks and rolls, this guy is pretty much stable. But I don't think they ever built it. Now I know that somebody here is thinking, oh, this is wonderful, I will build it. Because you're that kind of people. Ultimately, I think that the reason was that, well, Galileo had other problems. The church apparently didn't like the idea of Jupiter having moons in the first place. It didn't fit with the Bible, so Galileo was busy with being in jail and stuff. One way that kind of worked was the method of lunar distance. It was the idea that if you look at the moon and you calculate the distance between the moon and the sun, for example, or some specific star, from there, you can calculate your longitude. The problem with that is that that distance is always changing, so you need to deploy and update tables such as this one. This is from 1911. They kept doing this for quite a long time. They were not very precise and kind of hard to use. You can see the distance from the sun, from Aldebaran, from different, producing these tables was a mess. They had to use what we would call today massively parallel supercomputing, and which means that they took, I don't know, a few people, like 20 people who were good at doing math, they set them in a room and they calculated the rest of, like forever, every day. And they tried to come up with this, but they were still not very precise. So in the end, they solved the problem finally at the end of the 18th century. And the solution was, kind of unsurprisingly, a better clock. They finally managed to build a clock that could be taken on a ship and just miss a few seconds in a day. This guy did it, John Harrison, an Englishman. One of the reasons why I like this story, by the way, is that this is the triumph of geekness over capital S science. Because there were people who were saying, oh, you will never build a clock that is precise enough. All the big scientists like Newton there, okay? You see Newton, slick guy, deep eyes, burning with the fire of science, and he was like, you will never do it. And look at that guy. He's like, oh, I didn't know it was impossible, so I just did it. He's a geek. Mr. Gravity. So you can take this story, okay? You can take this huge human adventure and try to put it on a line like this. You can say there was magic, then we had that reckoning, then, okay, we were looking at the stars, and then we found clocks. But actually, this is not how it worked. These methods coexisted there were still lunar tables in the 20th century. They were replaced not by clocks, but by radio waves, which in a way means that you remember those guys with the dog, long-distance communication, that actually, they were right. And then we had GPS. So the people who said, just look at the sky, in a way, if they were on Reddit today, they would say, oh, I was right. It's more like this. This is progress. It's a cloud of confusion. It's a mess of things that exist together. Things that intersect, and they fork, and they replace each other, and they come and go from other disciplines. It's an evolutionary battlefield, okay? It's a Darwinian thing. There is one thing that's important in evolution, that it's not about the best thing, the best technology, the best way to calculate longitude, the best programming language. Best means nothing when it comes to evolution. It's about being the fittest to the contest. If you think that the best technology wins, ask the small talk people. It doesn't. It's about being fittest to the context, and the context is always changing. So there are a few things happening in evolution that are interesting, a few patterns, let's say, okay? One is that adaptations can be unexpected. You don't always see where things are going. Here is an example. This little cute guy here is our ancestor. Say hello to Grandpa. Seriously, say hello to... Oh, thank you. Yes. He was about this large, okay? Grandpa was a fish, of course, but he was a fish with a plan, spending more and more time on land. And if you look at him, you can kind of see that, you can see that we are relatives. I mean, his face is not so different than ours, and you can see that his fins became our limbs, basically. Other things are harder to see. Where do lungs come from? Our lungs. Fishes have a thing that's called the swim bladder. They use it to float higher and lower in water. And that's where lungs come from. What happened to his gills once he moved on land? Where are those gills now? Apparently, Grandpa found that once he didn't need gills to breathe, he could just use them to make noises. And, well, ever wondered where your vocal cords come from? Now you know. And this is happening again and again. If you think that you see the consequences of things, sometimes those consequences are quite far removed. Let's make an example by saying, why functional languages? Why should functional languages be the next big thing? The original reason for that is that functional languages have immutable data. Okay? If you look at a pure functional language, it doesn't have variables. Data is immutable. If you have a list and you add an element to the list, you get an entirely new list. So let's see an example in this LISP syntax, closure-y, if you wish. It's a silly formula for calculating how happy you are. Basically, whenever you see parentheses, this means this is a function, okay? And the first thing in the parentheses is the name of the function, and the rest is the parameters of the function. So this is the sum of two things. And the first thing is the multiplication of the smiles you received in the latest 10 minutes by the friends around you. Silly stuff, never mind, just something random. And this gets added with the ideas you had today, okay? These are functions, so you can look inside the functions and expand them. So, for example, how do you calculate the ideas you had today? I'm assuming that there is a list of ideas you have every hour, and it's in a reverse chronological order, so you just take the last 24 of those and you add them together. Well, phew. Not important that you understand the details. What's important to understand is what happens to those functions. How does an interpreter evaluate those functions? Well, one thing that you can do is think, well, there are only mutable data, right? Every piece of data is immutable. So what happens to the word, to the state of the word after you execute a function? It doesn't change. It cannot change. Everything is immutable. So basically, if you execute a function once or twice or never, it's stateless. Okay? This means that you don't have to worry when and how many times a function is actually calculated. You just worry that it's calculated, which means that you have something that you can just take the result of the function and replace the function with its result. It's called the referential transparency, if you are into that. So I can just replace those functions. For example, the to take functions, I replace them with an array, their result. I can go on doing that. For example, let's replace the first call to plus on the array. Oh, no, sorry. Let's replace the count now. Okay? That's the result of the count. I can do that in any order. I can replace the first call to plus, the second call to plus here, and go on like that until I get the result, okay? That's just a coin step. And now, let's go back. Look at this. We came to the conclusion that you can just replace these functions with their result in any order. It doesn't matter. If you look at the parentheses, you will immediately know when you can do that. So you can take these functions and resolve them in different moments, even in different places. Like those three, you can replace the first one, and then the second one, and then the third one, or you can actually replace them on different computers. You can send them to different computers and let them replace them, and then get the result back. So let's recap. We have immutable data. Because we have immutable data, we have pure functions. Because we have pure functions, we can replace a function with the result of the function. That's referential transparency. Because of that, you can decompose the functions. A mathematician would not agree with that, but screw them. And because of that, you have parallel programming. So you see the long-term consequences of one design decision, have immutable data. Parallel programming is a big deal these days. We have multi-cores and so on. That's why Lisp is suddenly fashionable again. It's the next big thing, you say. There is this is the effect of unexpected adaptations. There is another story about this. It's Russ Olsen told me this story. You probably know Russ Olsen. He wrote Eloquent Ruby. It's an amazing book. Many people on the internet think that it's a better book than my book. Those people are wrong. But anyway, it's awesome, and he's an awesome guy. And the story was that he wanted to learn Clojure, which is a functional language. So he decided to write a Forth compiler in Clojure. Forth is a weird little language that is based on a stack. Basically, it's very easy to write a compiler for, try it. Basically, the entire word is a big stack, okay? So he was creating stacks as he was executing Forth code. And at one point, he had bugs in his Forth code, and he wanted a debugger. And he thought, hey, everything is mutable, so I'm never really changing a stack. I'm just creating new stacks. So I can put all these stacks in a list and just go through the stacks in order. And then he made a list with all the stacks, which were the states of the program. And at that point, he thought, oh, wow, I can actually walk it in the other direction. I can rewind my program. he could debug back in time, okay? It's like imagine a programming language with an undo keyword. Don't do that. But basically, that was it. This is an example of what happens when you make a design choice that is radically different. Speaking of which, another about design choices, another pattern that happens in evolution, it's evolutionary dead ends. Okay, imagine being a mammoth, and the world is getting warmer. What do you do? Yeah, you die. What do you do? That's what happens. So, speaking of which, do you have any suggestion for an evolutionary dead end in software? Windows, wishful thinking. Flash, maybe. Anything else? Privacy, that hurts. Prolog. Prolog, don't count on it. I mean, I spent most of my 20s poking fun at people using VI. I was like, caveman. And now what are you using now? So now the joke's on me, right? Don't poke fun at Prolog. You never know what happens. COBOL. Perl. Okay, I have one. I have one. Think about static and dynamic typing. I won't go into that, but there is one specific technology related to static typing that I think was an evolutionary dead end, and that was SOAP. Okay? This is what I call the tragedy of SOAP. It's a tragedy because it took so much effort and training and a huge investment, and it didn't work. My own personal evolutionary explanation of why it didn't fit the context. What's static typing, really? Well, you have two parts of the systems talking to each other. They might be small objects, they might be huge servers or whatever, but we usually call that side the client, the side initiating the conversation, and the other side the server. So they need to talk to each other. So, of course, they want to understand each other. You always need that understanding. So you have some kind of contract saying you can call this procedure, and this procedure is taking a string and an integer. Now, the question is how much of that contract should be explicit? How much of it should be in your language? For example, a language like Forth that I named earlier has basically no explicit contract. You just call a function, procedure, and you don't even pass parameters. The procedure will go out and fetch those parameters from the stack. Ruby is a little bit more demanding, strict in this respect. So you have to say, here is the function, and it has two parameters. I won't tell you what they are, but there are two. This is what we usually call dynamic typing. And then Java, for example, has more explicit contract. So it says two parameters, a string and an integer. And Ruby and Java are actually quite close, because there are languages that are much more strict. Like a language named Eiffel says, this is a string, and it cannot be null, and an integer which must be greater than 10. So basically, it's about being more and more explicit. What's the point of being more explicit in the language about this? Basically, the idea is that you can have a machine analyze your code and find that, for example, one of the two parts is not sticking to the contract. So you can build this machine, this benign entity called Bob. Let's call him Bob. And Bob will look at your code very early, even before your code runs, and say, oh, no, you're not sticking to the contract. Of course, you need to have Bob. If you don't have Bob, then there is not much of a point in being more explicit in your code. That's the reason why dynamic languages are usually interpreted, and statically typed languages are usually compiled. Because if you don't have the Java compiler, the C linker, some kind of bobness, then you don't really have any advantage out of that. And the idea of SOAP was, let's put static typing on the network. And on the network, there is now Bob. So the idea was flawed since the very beginning. You can call me out on that. But I think that it was an evolutionary dead end because it didn't recognize that the context was completely different. That's about evolutionary dead ends. I have one last thing. This is going to be quick. There is another thing happening in evolution that is called divergent evolution. This is the way that species are born. You start getting more and more different, and suddenly you cannot mate anymore. Can you imagine an example of this in software? Sorry? This is interesting. Unix distributions? Okay. Repository forking. Wow, that's insightful, guys. Okay, stop it. I was thinking about something else. I'm kind of apparently you came up with better suggestions. I was thinking about the object-relational mismatch, which is amazing because basically we have relational databases, okay, and we decided that they were good. And then we had object-oriented programming, and we decided it was good. And they don't mix. And we are complaining all the time about this. We've been fighting with this for a very long time. And if you think about it, it's frustrating. We created this problem. It didn't exist. We made this problem. It's like somebody coming to you and say, I have a food problem. Fried squids and strawberry jam together, it tastes like shit. Well, don't put strawberry jam on your squids. And we tried every possible way to overcome this problem. So, for example, we tried object-relational mappers like Hibernate, which is huge and very complex. And if you use it, then it's probably going to be the most complex piece of software in your entire system, just to try and solve a problem that didn't need to exist in the first place. Okay? I was in the Hibernate core team. I'm guilty of that. It didn't really work. I cannot say it worked. It still tastes like squids with strawberry jam. And another guy, interestingly, some other guy said, oh, we will make this thing called active record, called Rails. Imagine rewinding the clock now and talking to DHH and his friends. And they go like, oh, we want to build a web application. And you are like, OK, you're lucky, guys. There are like thousands of web frameworks on the internet, and you can just download one and get going. Oh, no, we will write our own framework for that. And while we are at it, we will use a language that almost nobody knows. And most of the documentation is in Japanese. We will also base the entire framework on at least the database part, on a pattern that proved simplistic multiple times in the past, and never worked so far. What do you tell these guys? It's the most stupid idea ever, right? Frankly, I would have said no, fail, and it worked. That's why I say, don't ask me about computers. I don't understand that stuff. So this is what evolution looks like. Unexpected adaptations and dead ends, stuff that forks and doesn't want to come together, stuff that seems to die and then comes back after a few years, everything in this cloud of confusion, which takes us to the problem. What do I do now? What kind of strategy should I use when I'm in the cloud and I don't know what to do? What can I do if I live in a world where people can decide to just write another web framework based on very shaky foundations, and it happens to take over the world? It happens to work much better than anything else. It's very depressing, actually. We're supposed to know. People come to us, oh, what kind of technology should I use? And we don't know. We don't know shit. Which takes me to the title of this speech, which is Hunters and Gatherers. A hunter is focused. A hunter is opinionated. A hunter is a person who has a strategy of applying one idea to the extreme consequences of it. So, for example, hunting gave us rails. They had an idea, they were opinionated, they pushed it as far as they could. It worked great. But hunting also gave us soap. Gathering means you take what's there. You don't have strong opinions. You use whatever. So a hunter is focused on one track. He follows one strong opinion, and the gatherer takes whatever is there. And of course, the problem with gathering is that you don't innovate if you gather. If you don't try out new stuff, you never innovate. On the other hand, the problem with hunting is soap, or whatever is there. So what should you do? This is the big question mark. I've been doing this for a long time, and I'm kind of lost here. There is one thing that you could do. It's like a mantra. It comes from Paul Sappho, who is a futurist in Palo Alto. It's this slogan that I found absolutely beautiful that says, strong opinions weakly held. Which means you should have strong opinions. If you don't have strong opinions, you will never innovate. You should stick to your ideas and see how far you can push it, even if it's stupid, because mistakes are productive. I mean, think of Columbus. He did everything wrong, and what do you get for that? Instead of dying, like you deserve, frankly, you get your beautiful monument at the end of the Ramblas or somewhere. And there are so many examples of things working fine, even if they are very out there. And so you should have strong opinions, but don't get too attached to your opinions. You are not your opinions. Don't identify yourself with those opinions. Be ready to change them for another opinion that is very strong and uncompromising, because this is what works in a very complex environment like software development or innovation in general. I think that this is awesome. It's like a guideline in a very confusing world, and I actually believe that this community does it right. This is almost like the unspoken slogan of the Ruby community. Strong opinions weakly held. I remember once I went back to Ruby after some time off, and I wanted to use, I can't remember which technology, maybe it was Mechanize or WebRat, something, and I started using it, and it was bugged. And I tried to I issued the pull request, and nobody cared. And I tweeted about it, guys, I mean, it's supposed to be an essential piece of the stack, and nobody seems to care that it's not working. And people on Twitter were like, oh man, you're so last week. We're not using that anymore. Now we are all using this other thing. Okay. It happens again and again. Think about how long did it take for the entire community to move over to GitHub. Does anybody even remember Ruby Forge? This is what the Ruby community does very well. There is one strong opinion, one or two or three big ways to do things. And people fight for them, except they can change their mind almost overnight. So they adapt. Actually, I would say that as long as the community can keep doing this, it will keep doing well. This is why things are happening in the Ruby community. It's a good evolutionary battlefield. So if you can have strong opinions and not get too attached to them, I would say that you will do well. For what it's worth, I really think that you're doing a pretty good job. Enjoy the conference. Thank you. I will repeat it.
Talk about two groups of people. One of those groups invents new stuff, and another one uses the already invented stuff. What about people who combine existing solutions in an experiment?
When I say, the question is, you talked about hunters and gatherers, and hunters are the inventors, and the gatherers are basically combining what exists, using what exists. And the question is, what about people who can take existing inventions and mix them together? Actually, I wasn't talking about two separate groups. Hunters and gatherers are just two fictional characters. They are just like voices on your shoulders, okay? So you have the hunter, stick to that, and the gatherer, who cares? It's stuff like that. And this dialogue ultimately makes your choices. So when you combine existing, there is look, I don't want to bore you with a lot of theory, but basically this idea that science does not just accumulate is from the 60s. It comes from a book that's called The Structure of Scientific Revolutions, that basically said that what we have is always a bunch of stuff that we combine. That's one of the things that I think, if I interpret the book correctly, it's quite a heavy read. Pretty much everything you do is based on what happened before. That's actually the main notion of innovation. For example, there is a book on longitude that calls John Harrison, the guy who invented this good clock, a lone genius. I don't think that lone geniuses exist. I think it's an oxymoron. He was just perfecting stuff that existed. So everybody is always putting together stuff that already exists, including this presentation. I personally never had a single idea in my entire life. I just steal them. You're welcome. Does it answer your question? It's fluffy, right? A keynote. Sorry? It's a book by a guy called Kuhn, The Structure of Scientific Revolutions. It's really hard to read because of the style. It's terribly academic. But if you can find a wrap-up, there are wrap-ups on the internet that are worth browsing through.
Please put your hands together for Paolo.
Thank you.